Nuclear forensic characterization enables the gathering of information about nuclear materials and their origin. This information includes the type of nuclear power plant the material came from, its history and age. To better understand this connection between isotopic ratio of the fuel and the reactor design, let's recall some of the main features of a nuclear power plant and the differences between the various reactor types. Depending on their design, nuclear power plants differ in their degree of fuel enrichment, choice of coolant and neutron moderator. The general principle of power generation is the same for all types of nuclear power plants. In the reactor, a controlled nuclear chain reaction is maintained by neutron-induced fission of atomic nuclei. By energy transfer, the fission and decay products heat the coolant, which in turn drives a steam generator. A steam turbine converts the heat contained in the steam into mechanical energy, and a generator converts this into electrical energy. In order to maintain the nuclear chain reaction in the reactor, each fission has to cause on average one or more subsequent fissions. For example, the neutron-induced fission of uranium-235 into barium and krypton releases on average 2.3 neutrons, which are then available for further reactions. Nuclear fuel is made of natural uranium that is composed of the isotopes uranium-234, 235 and 238. Of these, only uranium-235, whose abundance is around 0.7%, is fissile by thermal neutrons. Therefore, for use in most reactor types, natural uranium must be enriched prior to fuel fabrication. The degree of fuel enrichment differs for different reactor types. Other nuclear reactions contribute to the energy production too. For example, when a uranium-238 nucleus absorbs a thermal neutron, an N-gamma reaction takes place and uranium-238 is converted into uranium-239. Due to two subsequent Be decays, the fissile plutonium-239 is produced. This phenomenon is called breeding. Fission of uranium-235 or plutonium-239 generates fast neutrons with a kinetic energy of several megaelectronvolts. They have to be cooled down to thermal energies to continue the nuclear chain reaction, because the cross-section for neutron-induced fission of uranium-235 is 3 orders of magnitude higher for thermal neutrons than for fast ones. Fast neutrons are cooled down due to a transfer of their kinetic energy by elastic collisions with other nuclei. The energy transfer is most efficient for nuclei of equal mass, therefore materials with a high density of light nuclei such as water are chosen as the moderator. Reactor designs differ according to their moderator and coolant. In civil energy production, mainly graphite-moderated reactors, light water reactors and heavy water reactors are used. The most prominent design of graphite-moderated reactors is the pressurized tube boiling reactor, also known as RBMK, which was developed and built by the former Soviet Union. A fundamental difference in the design of RBMK reactors compared to the Western reactors is that there is no physical containment surrounding the reactor core in an RBMK. RBMK reactors are operated with uranium dioxide fuel with a uranium-235 enrichment grade of 2.0 to 2.8%. The fuel is contained in silk alloy pressure tubes, which are embedded in the graphite moderator block. Ordinary water is used as the coolant. The RBMK reactors became sadly famous due to the Chernobyl accident. After the accident, additional safety precautions were applied to the remaining RBMK reactors in order to improve the operating safety. An example of heavy water reactors that use dehydrated water for both coolant and moderator are the CANDU reactors, which were developed by Canadian companies. The fuel in CANDU reactors is also contained in individual pressurized tubes, which are flowed by the coolant. The advantage of this design is that the production of smaller pressure tubes is more straightforward than the production of a large pressure vessel. The absorption cross-section for thermal neutrons of deuterons is 3 orders of magnitude smaller as compared to protons, making heavy water a superior moderator. As a result, fewer neutrons are absorbed by the moderator, and therefore heavy water reactors can be operated with natural uranium. In the context of non-proliferation, pressurized tube reactors like CANDU and RBMK reactors have to be considered critically. Since these reactors are designed in order to allow the replacement of fuel elements during power generation. Thus, it is possible to replace the fuel after a short irradiation time and thereby obtain weapon-grade plutonium-239. Today, about 85% of the world's nuclear energy is produced by light water reactors. There are two major types of light water reactors: pressurized water reactors and boiling water reactors. In order to reach criticality in a light water reactor, the fuel has to be enriched to about 3% of uranium-235 to compensate the neutron deficit due to the larger capture cross-section of hydrogen compared to deuterium. Pressurized water reactors are the most widely used reactors in the world. In contrast to boiling water reactors, they have two separate water loops. The water in the primary loop flows through the reactor core and serves simultaneously as moderator and coolant. The water is pumped into the steam generator, where the heat is transferred to the secondary loop that drives the steam turbine. The advantage of two separate water loops is that the secondary loop is free of radioactivity, thus simplifying the maintenance of the steam turbine. As this brief overview of three different reactor designs shows, if a fuel pellet is illicitly trafficked and seized, its degree of enrichment enables identification of the type of reactor it came from. Moreover, the type of reactor can be further limited by the geometry and other physical characteristics, since the fuel elements are specific for each reactor type. This table summarizes the basic technical characteristics of the reactor designs just presented. For example, the fuel pellets of a CANDU and RBMK reactor are significantly larger than those of pressurized water reactors. However, these two can be easily distinguished by their degree of enrichment, since CANDU reactors are operated with natural uranium in contrast to RBMKs. If a fuel pellet that has already been irradiated in a reactor is seized, the irradiation time can be estimated by its elemental composition and the different isotope ratios. In reactors loaded with low enriched uranium, after the burnup, the initial uranium-235 abundance decreases from 3% to about 0.8%. Due to the already mentioned neutron capture of uranium, long-lived plutonium isotopes are produced, and their concentration increases to an abundance of about 0.9%, and that of other fission products to about 3.4%. The ratio of plutonium-240 to plutonium-239 is also of major interest to nuclear forensic scientists. Indeed, this ratio increases the longer the fuel is irradiated in the reactor, because plutonium-239 can not only be fissioned by neutrons, but can also react to plutonium-240 by an N-gamma reaction. The ratio also depends on reactor characteristics like the neutron flux that passes the reactor core, which permits an assignment of the ratio to a specific reactor design. The radiochemists can support nuclear forensic investigations by collecting data concerning the chemical and isotopic composition of nuclear materials to provide information about their intended use and origin.